Okay, so now we look at 8.2. Really, we're doing the same stuff as in 8.1. We're talking about inconsistent and dependent systems. The meaning of that is that inconsistent is a system with no solution. Dependent is one with infinitely many solutions. So we use Gaussian elimination to solve this system. It's the same sort of stuff as what we did in 8.1. So I have a 1x, 2x, and a 3x. So my first column will say 1, 2, 3. A negative 2y, a negative 3y, and a negative 4y. So that's negative 2, negative 3, negative 4. And then the z's are all negative 1s, at least the coefficients are. We don't know what the value of z is yet, but the coefficients are all negative 1. And on the right side, negative 5, 0, 1. Okay. So we are happy to have a 1 in the top left place, but we would like to see zeros below it. If we have an equation with a 1x and a 2x, we could multiply the top equation by negative 2 and add it to the second. In the matrix, negative 2 row 1 plus row 2. With a 1x and a 3x, we could multiply the top equation by negative 3 and add it to the third. In the matrix, negative 3 of row 1 plus row 3. So we've eliminated x twice by doing this, and we're going to write those new equations as rows 2 and 3. Row 1 remains the same. And we've eliminated x in our new equations. So let's see what the results are for y and z in the right side. Looking at row 2, it's negative 2 of row 1 plus row 2. Negative 2 times negative 2 is 4. Minus 3 is 1. In the z column, negative 2 times negative 1 is 2, minus 1 is 1. On the right side, negative 2 times negative 5 is 10, plus 0 is 10. In other words, by eliminating x in the first two equations, I've created the equation y plus z equals 10. Now we look at how we eliminated x in the first and third equations. Going to the y column, negative 3 times negative 2 is 6, minus 4 is 2. In the z column, negative 3 times negative 1 is 3, minus 1 is 2. On the right side, negative 3 times negative 5 is 15, plus 1 is 16. And so by eliminating x with the first and third equations, I've created the equation 2y plus 2z equals 16. We're happy with the first column now. We'd like the second column to start with a 1 on the, at least in the second entry. So we have a 1 going down the diagonal. So we would like to have a 0 below this 1. In other words, we have a 1y and a 2y, and we'd like to eliminate y. So let's run a negative 2 through the second row and add it to the third. That would give us a negative 2y plus 2y, which would eliminate the y's. Note that the first row isn't in this step, so we're going to rewrite the first row. The second row is only being used as a tool to change the third, so I'm going to rewrite the second row. In the third row, the first column is unchanged. I mean, all the progress we've made remains. Negative 2 times 1 is negative 2, plus 2 is 0. In the z column, negative 2 times 1 is negative 2, plus 2 is 0. On the right side, negative 2 times 10 is negative 20, plus 16 is negative 4. So the third row has 0x plus 0y plus 0z on the left side. In other words, the left side is 0, but the right side is negative 4. 0 doesn't equal negative 4 ever, and so we conclude that this system has no solution. In the next example, we look at a system of equations that's going to have infinitely many solutions. Starts out the same way. We see that the x's have a 1, 2, and 1 in front of them. For the y's, the coefficients are negative 2, negative 5, and negative 3. For the z's, the coefficients are negative 1, 3, and 4. and the right side is 5, 6, 1. We have a 1 in the top left, so we're happy about that. To eliminate the 2, let's take negative 2 of row 1 plus row 2. To eliminate the 1 in row 3, let's take negative row 1 plus row 3. The first row is merely a tool to change the second and third, so I'm going to rewrite it. The second and third rows' x coefficients are 0. We eliminated x in that step. So let's see what remains for y, z in the right side. For the second row, so we're doing negative 2 of row 1 plus row 2. Negative 2 times negative 2 is 4. Minus 5 is negative 1. Negative 2 times negative 1 is 2. Plus 3 is 5. On the right side, negative 2 times 5 is negative 10. Plus 6 is negative 4. Looking at the third row, we're doing negative row 1 plus row 3. Negative 2 is 2. Minus 3 is negative 1. In the z column, negative 1 is 1. Plus 4 is 5. On the right side, negative 6 plus 1 is negative 5. Let's see, just thinking, I have a mistake. Let me just search that out here. So if I've got, oh sorry, here's the mistake I made. It's this negative 5. It's negative row 1 plus row 3. Sorry about that. Negative 5 plus 1 is negative 4. There we go. Okay. So next we need to see a 1. In going down the diagonal we need 1s. So this negative 1 needs to be changed into a positive 1. So let's run a negative through row 2. That's not going to affect rows 1 or 3. So I'm just rewriting those. And I'm changing all the signs in row 2. After all, I'm multiplying them by negative 1. So that's 0, 1, negative 5, and 4. I've changed all the signs in row 2. I have my 1 going down the diagonal. Now I'd like a 0 below this. Well, 1 and negative 1 already add to 0, so let's do row 2 plus row 3. Row 1, not mentioned here, so I'm just going to rewrite it as it was. Row 2 is being used to change row 3. After all, we're happy with row 2. It's got the 1 in that diagonal place. Well, when we add up the entries of row 2 and row 3, I mean, they all cancel out. 1 minus 1 is 0. Negative 5 and 5 is 0. 4 minus 4 is 0. So the third equation says 0 equals 0. Well, that's always true. And so we would conclude that there are infinitely many solutions. Now this conclusion isn't sufficient. We have to say, well, what are the solutions? We can't just plug in any 3 numbers. There are infinitely many triples of numbers. It's just they can't just be anything. Okay. So the way we would work this out now is let's jump into row 2. So row 2 says 1y minus 5z equals 4. Well, to solve for y, as I usually do in row 2, let's add 5z. And so y is 5z plus 4. Next we go into row 1. Row 1 says 1x minus 2y minus z equals 5. So let's write that down. Now y happens to be 5z plus 4, so that's x minus 2 times 5z plus 4 minus z equals 5. Let's distribute negative 2 to get x minus 10z minus 8 minus z equals 5. And we see that there's like terms here. Negative 10z minus z is negative 11z. So I have x minus 11z minus 8 equals 5. And in row 1 we solve for x, so let's add 11z and 8 to both sides. So 11z goes to the right side, 8 and 5 makes 13. Now when we write the solution of a system of equations, we write it as an ordered triple, x, y, z. Okay, so let's do that here. X is 11z plus 13, y is 5z plus 4, and then you just have z. The idea here, this does represent infinitely many solutions. Pick any number for z, then to solve the system, x had better be 11 times that number plus 13, and y had better be 5 times that number plus 4. So you have complete freedom with z, but then x and y fall into these patterns. In the next example, we look at what's called a non-square system. Non-square means the number of equations and the number of variables is not the same number. But we can still use Gaussian elimination, i.e. matrices, to solve these systems of equations. So we're going to have two rows because we have two equations. We have a 1x and a 1x, a 2y and a 1y, a 3z and a 1z, and then 70 and 60 on the right side. So I'm happy to have a 1 on the top part of the diagonal, and note that the diagonal is a bit truncated here. I mean, we don't have a third row to sort of complete the diagonal, but we work with what we have. Now you might say, aren't we happy that we have 1s on the diagonal, so we're done? Well, the thing is, you do want 1s on the diagonal, but you want 0s below them. So I need this to be a 0. So I can take the negative of row 1 plus row 2. That would make negative 1 plus 1, which is 0. As usual, the first row is being used to change the second. So I'm just going to rewrite the first as it was. Now let's run through and do negative row 1 plus row 2. Negative 1 and 1 makes 0. Negative 2 and 1 makes negative 1. Negative 3 and 1 makes negative 2. Negative 70 and 60 makes negative 10. I mean, this is what we're doing. We're taking a negative through the first equation and adding the equations together, giving us a new equation, negative y minus 2z equals negative 10. Well, now we would like to see the next element in the diagonal be a positive 1. If it's currently a negative 1, let's run a negative 1 through that row. The first row is unaffected by this. The second row, we're changing the signs because I'm multiplying by negative 1. Well, we've got 1s on the diagonal, 0s below them. That means we're done with this matrix. The second row says that y plus 2z is equal to 10. Therefore, y is equal to 10 minus 2z. In the first row, we have x plus 2y plus 3z equals 70. Well, y happens to be 10 minus 2z, so that's x plus 2 times 10 minus 2z plus 3z equals 70. And now let's distribute the 2. X plus 20 minus 4z plus 3z equals 70. We can note now that negative 4z and 3z makes negative 1z. So I've got x plus 20 minus z equals 70. And in row 1 we solve for x. So let's subtract 20 and add z. If I subtract 20 from 70, that's 50. And then I'm adding z. So the ordered triple that solves this system of equations, I have infinitely many of them. the x is 50 plus z, the y is 10 minus 2z, and then we have z itself. Again, we have complete freedom to choose z, but after that, x and y have to follow these formulas in order to solve the system. So we can't just pick any number we want. In the last example, we look at an application, so a traffic flow problem. So this figure shows a system of 4 one-way streets. The numbers in the figure denote the number of cars per minute that travel in the direction shown. So just to sort of show what's going on here, so this is called intersection 1. We see that this street is traveling north only, okay, and we have a street traveling east only. So intersection 1 deals with those two streets. Looks like there's W cars headed north away from intersection 1 per minute. There's 10 cars headed north toward intersection 1 per minute. 5 cars headed east toward intersection 1 per minute. And Z cars heading away from intersection 1 per minute. In part A, we use the requirement that the number of cars entering each of the intersections per minute must equal the number of cars leaving per minute to set up a system of equations in W, X, Y, and Z. That's not an arbitrary requirement. A lot of times in math problems we see such arbitrary requirements, but the idea here is for ideal traffic flow, we want the number of cars entering and leaving to be the same per minute. So in part A, we're going to set up a little chart. So it's going to have 4 columns and 4 rows. So let's set up equations that describe what's entering and leaving each intersection per minute. So in intersection 1, we see arrows pointing at that intersection. There's 5 cars entering from the west per minute and 10 entering from the south per minute. So I'm seeing a total of 15 cars entering intersection 1 per minute. Heading away from intersection 1 going north, there's W cars per minute. Heading away from intersection 1 going east are Z cars per minute. So leaving are W plus Z cars per minute. In order to keep traffic flowing, then, we would want W plus Z to equal 15. The number of cars entering and leaving are the same per minute. In intersection 2, this time the numbers are pointing away from intersection 2, or the intersection. 10 going west away from intersection 2, 20 going north away from intersection 2. So looks like there's a total of 30 cars per minute leaving intersection 2. Now headed toward intersection 2, we see that there are W cars headed north toward intersection 2, X cars headed west toward intersection 2. So there's a total of W plus X cars per minute entering intersection 2. And so in order to keep traffic flowing optimally, we want W plus X to be 30, so that entering and leaving is the same number. Looking at intersection 3, the 15 and the 30 are pointing at the intersection. So there's a total of 45 cars entering intersection 3 per minute. Heading away from intersection 3, we have X cars traveling west away from intersection 3, and Y cars traveling south away from intersection 3, for a total of X plus Y cars per minute. And so we'd like X plus Y to be 45. Finally, in intersection 4, the 10 and the 20 are pointed away from the intersection, so there's a total of 30 cars leaving intersection 4 per minute. Now entering intersection 4, well, we see Y cars traveling south toward intersection 4, and Z cars traveling east toward intersection 4, for a total of y plus z cars. And so we would like y plus z to be 30. These four equations in the fourth column are the answer to part A. It says to set up a system of equations, and we've now done that. Now in part B, we use Gaussian elimination to solve this system. So let's set up a matrix. The first column will be dedicated to the w's, then x, then y, then z. So if I list the coefficients of the w's going down the line here of my equations, 1w, 1w, no w's, no w's. So my w column will start as 1, 1, 0, 0. Next we go to the x column. So no x's in equation 1, 1x in equation 2, 1x in equation 3, no x's in equation 4. Going to the y column, no y's in equation 1, no y's in equation 2, 1y in equation 3 and 4. And for the z's, 1z, no z, no z, 1z. On the right sides we have 15, 30, 45, and 30. Okay, so although we have 1s on the diagonal, we want 0s below those 1s. So let's make that happen. I would like this 1 to be a 0, so I'm going to take negative row 1 plus row 2. So that creates that first column for me. The first row is only used to change the second, so it's not like I'm writing a new first row. The third and fourth rows are not mentioned in this calculation, so I'm just going to rewrite them as they were. To get the rest of the second row, we do negative row 1 plus row 2. Negative 0 plus 1 is 1. Negative 0 plus 0 is 0. Negative 1 plus 0 is negative 1. Negative 15 plus 30 is 15. Next we go to the second column. We've got our 1, but we'd like a 0 below it. So I can do negative row 2 plus row 3. Okay, so the first row is not mentioned here. The second row is only being used to change the third, so I'll rewrite the second row. The fourth row is also not mentioned here, so I'll just rewrite it as it was. For the third row, well, negative row 2 plus row 3. Negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 0 plus 1 is 1. Negative 1 is 1, plus 0 is 1. Negative 15 plus 45 is 30. Next, we have a 1 on our third diagonal piece, but we'd like a 0 below it. So I'll do a negative row 3 plus row 4. The first two rows are not mentioned at all, so I'm just going to rewrite them. The third row is being used to change the fourth row, so I'm just going to rewrite the third row. It's only the fourth row I want to change. And now let's do that change. Well, if we do negative row 3 plus row 4, the negative of all these plus these in row 4 would all cancel out. So to solve this system, we're finished with the matrix. We've gone as far as we can go. We've got ones down the diagonal and now a row of zeros. So the third row says that y plus z is 30. And therefore that y is 30 minus z. The second row says that x minus z is 15. Therefore, x is 15 plus z. The first row says w plus z equals 15. Therefore, w is 15 minus z. So let's go to the back here. So our solution then of this system, so continuing B, we have w was 15 minus z, x was 15 plus z, y was 30 minus z, and then we have z. So now in a way we can say that traffic flow depends on z. Okay, so in part C, it says if construction limits z to 10 cars per minute, how many cars per minute must pass between the other intersections to keep traffic flowing? So if we assume that we have these parameters, then w would be equal to 15 minus 10, since we're saying construction limits z to be 10, so w would be 5. X would be 15 plus 10, which is 25. Y is 30 minus z, so 30 minus 10, which is 20. And of course z is 10. Well, what do these mean? So for w to be 5, well, w is traveling from intersection 1 to intersection 2. So this is 5 cars per minute. Intersection 1 to intersection 2. So x is 25 cars per minute. And if we look on the front side, well, x is traveling from intersection 3 to intersection 2. So we would want 25 cars per minute traveling intersection 3 to intersection 2. Y is 20. Well, let's see, the meaning of y, we have cars traveling from intersection 3 to intersection 4. So we would have 20 cars per minute traveling from intersection 3 to intersection 4. And z is 10. Well, the meaning of z is down here, so that's going from intersection 1 to intersection 4. So it'd be 10 cars per minute traveling from intersection 1 to intersection 4. Thus concludes A2.